Open your codebase. Search for the number 768. You will likely find that exact integer hard-coded in 5 different programming languages across your project. Having your adaptive layout decisions scattered across independent files is an architectural failure masquerading as a best practice. Look closely at the drift pile. The layout logic lives in CSS. The resize listener lives in JavaScript. An ARIA attribute mirrors it in HTML. A uniform passes the state to a web GPU shader. A TypeScript union defines the types. When a routine redesign occurs, a developer updates the CSS breakpoint to 767. The JavaScript listener stays at 768. A single pixel of difference opens a gap between what the layout engine renders and what the rest of the application believes is happening. The consequences cascade directly into AI tooling. A prompt context file describes last week's layout rules, while the CSS renders today's. The generative model is blinded to reality, generating components for a state that no longer exists. Your UI probably has 5 responsive systems. LiteShip gives them 1 graph. An interface relying on scattered manual syncing is structurally untrustworthy. It is destined to lie. No amount of unit test coverage will save a system where the definition of reality is manually copy-pasted across independent execution environments. Modern CSS is a highly capable engine. Features like container queries successfully resolved the mechanics of rendering responsive layouts. The hard architectural limit is jurisdictional. CSS only owns the CSS surface. It has 0 authority to update accessibility states for a screen reader, and it cannot pipe logic into a web GPU computation. Container queries solved where a layout asks a question. They did absolutely nothing to fix how many different surfaces are required to answer it. When the visual state hides a navigation menu, but the ARIA attribute remains expanded due to a drifted integer, sighted users and assistive technology users receive completely different versions of interface truth. The application is lying to a portion of your audience. In a traditional backend system, a state mismatch throws an exception, alarms trip, execution halts. The deployment is rolled back and the error is addressed. Nothing crashed. That's the problem. Silent UI drift creates a deeply flawed ecosystem. The interface actively deceives the user without ever throwing a single error, turning what should be a precise state machine into a guessing game. A standard breakpoint is a fragile conditional statement trying to govern a noisy environment. The real world produces continuous signals. Viewport width slides, audio amplitude fluctuates, scroll positions drift. When a continuous signal hovers exactly on a discrete threshold line, the user interface flickers. The layout snaps back and forth as the incoming integer toggles around the boundary point. This diagram illustrates hysteresis. Electrical engineers solved signal bounce in the 1930s by placing a deliberate dead zone around the threshold. You enter a state at one line, but you only leave it when the signal climbs back past a different line. An adaptive boundary absorbs this noisy continuous signal, filters it through the dead zone, and outputs a stable, named state. This is the first assembly step of the LiteShip pipeline. We wire the raw, continuous signal directly into a boundary equipped with hysteresis. The resulting named state, like compact or spacious, is officially sealed into a structured document graph. The raw number is discarded. The semantic intent is preserved. Stabilizing the raw signal before it ever reaches a layout engine is the only mathematically sound way to build a reliable multi-surface state machine. The document graph is a content-addressed entity. It encodes the exact adaptive intent into canonical CBOR bytes and stamps it with an FNV1A hash. Sealing the intent means the definition cannot be tampered with by individual component files. The layout rule does not belong to the CSS file. The sealed graph is the ultimate authority. We see here the forward projection discipline, known as cast. The sealed graph acts as the single source of truth, and it fans out into specific output targets across the runtime. One single document graph definition automatically compiles down to CSS custom properties. The exact same definition simultaneously generates ARIA attributes and WGSL structs. There is no hand wiring required from the developer to sync these outputs. Casting guarantees flawless mathematical agreement between a screen reader, a GPU shader, and a CSS layout engine, because every surface reads from the exact same hash. The forward cast solves output, but users and systems eventually need to mutate UI state. Allowing manual mutations risks fracturing the sealed graph. The 0.7.0 architecture update introduces the client-to-server return leg. It establishes a unified path for state changes to travel back to the authority. This flowchart traces a graph patch. The graph is never mutated directly. Instead, the runtime only accepts typed, structured proposals, which arrive at a strict validation gate. The gate enforces a split path. It drops a refused patch entirely. If the patch is valid, it applies the change and immediately reseals the graph with a new content hash. If a patch carries a stale base address, it automatically triggers a refusal. This provides optimistic concurrency natively through the content address itself. AI generative models are subject to this exact same validation gate. They receive a mailbox to drop off proposals. They never receive root access to the UI. Patch is not an AI feature. Patch is the right protocol. It is the exact same door. It is the exact same law. Treating every human and AI edit as an untrusted proposal eliminates the risk of hallucinated or impossible UI states reaching the runtime environment. Operating a UI under a strict graph, cast, and patch pipeline yields a definitive result. With this content hash, we have expected projection. Output artifacts must match the graph's address. The outputs match the hash. If a rogue script bypasses the graph to alter an ARIA attribute, the output diverges. The system instantly flags this as drift. This architecture transforms silent UI drift from a subjective quality assurance vibe into a mechanically catchable type error. Turning adaptive state into a verifiable content hash elevates front-end development from fragile scripting into rigorous interface assurance. Define the boundary once, cast it to every surface, and admit changes only as validated patches. This pipeline permanently replaces the fragile pile of media queries, JavaScript listeners, and manual state mirrors that cause modern applications to silently break. LiteShip is a content-addressed adaptive UI runtime. It is not a CSS framework. Interface truth is no longer a scattered assumption hoping for agreement. It is a sealed, projected, and patched reality.